Have you ever dropped an iron nail into blue copper sulfate solution and noticed something magical? The blue color fades and a reddish brown layer starts to form on the nail. That simple experiment introduces us to an important concept, the displacement reaction. A displacement reaction occurs when a more reactive element kicks out a less reactive one from its compound. Chemically speaking, if we write a plus BC gives AC plus B, it means element A is displacing B from compound BC. For instance, zinc when added to copper sulfate solution reacts to form zinc sulfate and copper. This happens because zinc is more reactive than copper. Only a more reactive element has the chemical strength to replace another from a compound, and this concept finds immense application in both classroom chemistry and real-life industries like metal extraction. Now, how do we know which element can displace another? That's where the reactivity series comes into play. The reactivity series is like a leaderboard, ranking metals from most to least reactive. This helps us predict whether a displacement reaction is even possible. Take magnesium and copper sulfate, for example. Magnesium is higher than copper in the reactivity series, so it can displace copper, forming magnesium sulfate and copper metal. The reaction is Mg plus CuSO4 gives MgSO4 plus Cu. But if we flip it and try adding copper to zinc sulfate, nothing happens. Why? Because copper is lower in reactivity and can't replace zinc. So, understanding this series gives us a clear roadmap to predict the outcomes of such reactions. On screen, you'll see the reactivity series with key metals like zinc, magnesium, and copper highlighted. Do take a closer look. There are different shades to displacement reactions. The most common one you'll encounter is a single displacement reaction, where one element replaces another in a compound. A classic example is iron reacting with copper sulfate. Iron replaces copper and forms iron sulfate, written as Fe plus CuSO4 gives FeSO4 plus Cu. But metals can also displace hydrogen from acids. For instance, zinc reacts with hydrochloric acid to form zinc chloride and hydrogen gas. The balanced equation is Zn plus 2H close gives ZnCl2 plus H2. These reactions are not just textbook equations, they produce observable phenomena like gas bubbles and color change. In fact, a metal that sits high in the reactivity series can displace hydrogen from even water or steam, something we'll explore in later topics. Let's revisit that classic lab activity involving an iron nail and copper sulfate solution. You dip a clean iron nail into the bright blue CuSO4 solution, and over time, something fascinating happens. The nail begins to gather a reddish brown coating, that's copper, while the solution fades to a pale green as iron sulfate forms. What's happening at the molecular level? Iron atoms are displacing copper ions from the solution to form FeSO4, while copper atoms settle on the nail. The balanced chemical reaction is Fe plus CuSO4 gives FeSO4 plus Cu. This reaction doesn't just teach us chemistry, it visually proves the power of the reactivity series. You'll see on screen a diagram showing this experiment, iron nail partially coated in copper and the changing solution color. Displacement reactions aren't just confined to chemistry labs, they power real-world processes. In metallurgy, for example, iron is used to extract copper from copper sulfate solutions, making copper recovery efficient and economical. In corrosion science, we use zinc to coat iron in a process called galvanization. Zinc displaces oxygen and moisture first, preventing the iron underneath from rusting. One dramatic use is the thermite reaction used in railway track welding. In this reaction, aluminium reacts with iron oxide to form molten iron and aluminium oxide, releasing intense heat. The reaction goes 12 plus Fe2O3 gives to Fe plus Al2O3 and heat. You'll also find displacement at work in voltaic cells where redox reactions between metals generate electricity. Clearly, displacement reactions are both scientifically fascinating and practically vital. Let's solve a quick numerical to see how stoichiometry works in a displacement reaction. Suppose 6.5 grams of zinc react with excess copper sulfate solution. How much copper will be displaced? First, write the balanced reaction. Zn plus CuSO4 gives ZnSO4 plus Cu. From this, we know that 65 grams of zinc displace 63.5 grams of copper based on their molar masses. So for 6.5 grams of zinc, the copper displaced is calculated as 6.5 multiplied by 63.5 divided by 65, which gives us 6.35 grams of copper. This straightforward proportional calculation highlights how balanced chemical equations help us predict the outcomes of reactions quantitatively. Let's quickly go over what we've learned about displacement reactions. At the heart of it, displacement reactions are all about chemical strength, where a more reactive element ousts a less reactive one from its compound. The reactivity series helps us identify which reactions are likely to occur. We've seen examples involving metal displacement from salt solutions and hydrogen displacement from acids. From classroom experiments with iron nails to industrial processes like galvanization and thermite welding, these reactions are everywhere. The key takeaway: chemical reactivity is a driving force that transforms both test tubes and technologies. I hope this session helped you appreciate how a simple concept like displacement can have such wide ranging applications. Until next time, keep observing, keep questioning, and let chemistry keep unfolding around you.